become dampened. So you can have a situation where you have positive reinforcement, where they're going to meet like trough to trough or crest to crest, and they're going to reinforce that, or they're going to cancel that out. So if you ever listen to like Bose and they say, oh, it's noise canceling headphones, they're just trying to, what they're trying to do is cancel out that sound wave that's coming in, and in a manner like this, where you have one wave coming in, it hits the other one. The trough of one is basically going to hit the crest on the other one, and they're going to cancel each other out. So that's basically what they're trying to do. Okay, well done, Bruce. All right, back we go.
Is there a way to
No. Well, I suppose.
Yeah, we need to ask him about that.
Yeah.
Oh, yeah, Mr. Burkamp? Oh, I'll wait for you to come back. Who's all there? It's me, you, and Albert. People who aren't here. So we were at a Scholars Bowl meet yesterday, and we had a physics question. And so they were saying it was about the normal force, right? So they gave us the mass of the object, and they said it was just sitting on like a table,
Flat surface.
a flat surface,
Okay.
and they wanted how the amplitude and direction of the force, and the other team
Magnitude and direction.
said magnitude
Of which force?
of the normal force.
Okay.
And the other team said the right number, north. Would that be
And then
a
I was
correct?
really confused, so I challenged you. I was like, they should have set up,
Yeah.
and they were like, no, I'm pretty sure north is okay too.
No.
They were like, but if you think about like on a map, north is up, and I was like, yeah, but like north in the real world is towards the North Pole, not
Yeah.
up. And they were like,
Oh, I wouldn't have accepted it at all.
they said, so some
Because
girl
technically,
said that her
if
AP
they're
physics
right,
teacher used north.
Then I put this book here. That's north. The normal force is pointing that direction.
Which means it's gonna Harry Potter
Yes, it's
across
gonna
the
fly
room.
Across the room. No, completely wrong.
Yeah, it was that skull.
Yeah. We were like, we gotta ask Mr. Burkamp.
Completely wrong. I don't care what anybody says.
And we have it on record too now.
Okay. Yes, you do. Okay.
What was happening? I'm very.
What?
I want you to know that we named the Slinky Sir Isaac Noodle.
For what?
Isaac Noodle.
Oh, nice. I like that.
Very good. These are class pets.
Okay. Sir.
Sir Isaac.
Okay. Sir Isaac Noodle.
Oh wait, I'm still doing that.
Okay.
That's not what I know.
Okay, so this is the old school. Some of you have never maybe even seen a projector like this. Okay, but a lot of lecturers have them this way. So what?
She just okayed boomered you.
Does Mr. Burkamp even know what that means?
It seems he does.
For the record, I'm not a boomer.
It's just a very boomer thing to say, oh, you guys are probably too young to even know what this is.
Legitimately though, how many of you have seen? All right. Okay.
Okay, boomer.
All right. I used to like you.
Yes, I'm back to number one.
Yeah, don't get caught. You missed too much because of swimming. Okay, so we're going to look at this in a couple of different ways. So one option is that I've got like a wave like this, okay, and then I'm going to have another wave come in, and they're going to slide past each other. Now, imagine that I get to this point here, okay? Now, at that point there, where you've got the two troughs that are going to amplify each other, what's going to happen is that this would get real deep real fast because you have that energy that's on both sides pushing this down. So a lot of times, I don't know why AP gets this way, but they for whatever reason, somebody that writes the AP test really likes these kind of things. So basically, as you're coming along, at this point, so these would reinforce each other, and it would get deeper and deeper and deeper. And usually when it gets to that main point right here, then they would be able to say, oh, okay, right you have these two negative values, you basically you'd add these together, and you would get this really, really deep trough. But then as you keep going though, but then when you would hit a point like this, okay, where you would have this amplitude up here, and that amplitude down there, then what's going to happen?
Cancel out.
Then they'd cancel out, and then you'd end up with like no line at all. So, and that's typically what they do is they kind of play the extremes. And sometimes they'll see them drawn where you have like, sometimes they'll have like a square wave like this coming in, and then another square wave like this. And so if you have like that square wave up here and a square wave down here, then when they overlap each other, it's just like two hats that cancel each other out. But if you have two hats like this, then when they get in the middle, then you can get a lower, lower, tall hat. So you can either end up with like no hat or a lower, lower, tall hat, depending upon what they do with those amplitudes. But the main thing being is that then when they pass each other, after you get past that, then these waves are going to go back to being a normal situation where you're not going to have any kind of distortion at all, because the waves have just continued to go, and after the two waves pass in the night, then they're back to being normal. So basically, I'm only going to make you do like I think one or two on your assignment, because they're annoying. You're going to get the idea. If it's amplitude to amplitude, hey, it gets bigger. If it's amplitude to trough, it cancels each other out. That's the basic idea. Okay. So, I'm going to take my boomer projector, set that down. Liza dweeb.
Oh!
You got me there.
Well played.
Okay, I didn't start this, but I'll finish it. Okay. Now, so when you look at how musical instruments work, okay, can you give that a little bit of a swirl? So we have the Ames tube, and so there's two types of kind of resonant structures that you can have when you have musical instruments. You can have an open tube, which is what this is going to be. And then you can have an open closed tube, which is what I'll show you with the other one. So if you look at this one, and this works off of the, which one does this work off? The 880. So if we take that 880 one, okay, there we go. So what we're doing is we're making this thing vibrate within that system. So that's established this resonant structure, and so this one is what's known as an open tube, because oddly enough it's open on both sides. So, it'll only with that length, it'll only work with a particular frequency, because what you'll see is that it's based upon the wavelength of the sound. So if I try and do that same thing with an 883 hertz, okay, then it doesn't work, because it has to be specific to a particular frequency. Now, think about this. If I'm comparing an 880 hertz to an 883 hertz, so this one's 880, this one's 883. Which one is going to produce the shorter wavelength?
883.
The 880 or the 883?
883.
Why?
Because
they have an inverse relationship.
Because the two multiplied together have to multiply together to get you to the
speed of sound.
Speed of sound, right? Not the speed of light. So, sound.
Light. Sound without a medium.
Sound, whatever, yeah. So, as your frequency gets higher, your wavelength is going to get shorter. So, because of the fact that we're changing the frequency, we're changing the wavelength, and that's why it will only work with a particular length of tube. Because as you change the frequency, you change the wavelength of that sound that's resonating within that tube. So that's why it'll only work with a particular one. Now, the other thing that you can do, and this is that's what's known as an open tube. So if you go with this, okay, so now with this one, what I'm going to do is, and this is the lab that y'all are going to do on Tuesday. So I can change the height of the column. So what I'm going to do is I'm going to make this thing vibrate, okay? And what it's trying to do is it's sending a sound wave down. It's hitting the surface of the water, and then it's bouncing back up. So this is what's known as an open-close system, where this is an open-open system. So, and you'll see that the math is different on how you do the calculations.
Oh boy.
So on this one, okay, so if I lift this up, hold on. Okay,
Which right?
you'll hit that point. Where it reinforces that sound wave, but then if you go past that point, then you lose it again.
Is it because it's like a multiple of the length of the
Yes.
cylinder?
So
That's pretty
you're here,
cool.
you got nothing, you got nothing. There you go. So, but if I change that,
I thought
okay?
you was breaking glass over
Is that
there.
how they made the THC?
So now if I go, so that one that I did was 392, okay? So now I'm going to try it with the 880. So if you do a comparison, which one's going to have the longer wavelength? The
880.
392 or the 880?
Oh, 392.
392.
It's going to have longer wavelength. This is going to have the shorter wavelength. So now if I try it with this one, it might be too short to do with this one.
How do I do this?
So notice that that one gets that point of resonance at a shorter distance. Because it has a higher frequency, okay, then it's generating a shorter wavelength. So that's going to reinforce it at a shorter point, and that lower frequency, which is going to have longer wavelength, is going to reinforce it at a higher point. Yes?
What if we put them together?
What do you mean?
Both tuning forks at the same time?
No, it would just be chaos, okay? Because,
I like chaos. Let's do it.
well, I don't. I didn't vote. So,
Have you seen?
okay.
What entropy?
Don't listen.
No entropy, Ryan.
My Spotify playlist.
Too bad entropy's on the
Gregorian chant. Just
I know, but
simple
no
one
increasing
note
entropy.
But you're increasing it, Andrew.
And only, no, yeah, no words
Just
I
tuning forks. These
Sure.
recorded tuning forks. That's my Spotify playlist.
Also don't know how to do that problem.
That's
We'll let
how
it
they
straight.
use it. Like they did, they
Let me look at this real fast.
melodies.
No, we do it.
That's the Gregorian chant. Just singing.
We did that.
Wait, how do you do that?
No, we, no.
Yeah, and by the way,
They call it T.
I never put it together that Vonda was your sister.
Really?
Never did.
No?
But I'm trying to.
She
I
came up
understand
here
where-
yesterday
Yeah,
after school, we were talking, it's like, no way. Yeah, never put it together.
That's funny.
Yeah. She goes, well, my brother's in your class, like, who's your brother?
It should be 15 meters.
And I was like, seriously? Never even thought about it in any way, shape, or form.
Wow.
Never put that together. I
I
don't
like it.
Wait, I might have been Kim.
Technically,
Did
this.
you have it with
Think of the waves as fishes.
Yeah, because she said you were like in Chem 2 or, she said something about Chem 2, and that's kind of how I put it together.
I remember that. Yeah.
And
Oh,
This will make sense in just a second, and I'll go do a demo with it. So. Image on the side of the page.
So those are antonyms? No.
That was
You just realized?
that one well.
Ah, yes, the average of an antonyms.
I understand what a
That's
sonic
how-
boom
that's what
is
they-
now. It just
It literally, you literally break the sound barrier.
yeah,
Go faster.
because you
'Cause
catch
you're
up with all the
punching
sound
through it.
that you're putting ahead of you. You
Yeah.
catch up with
Yeah.
it and
Waving
punch
at
through
the-
it.
It's fancy.
Yeah, look. That's what it looks like after you.
Yeah.
And then it starts going like this. Then it starts going like as you're going fast.
Oh, how they just go behind you?
Its music is
Like the circles wave are opening.
Behind you.
Music is a cult.
It's time to
It
transcribe all
is.
the light and
You're
music
right.
sound.
It's kind
Yeah.
of tricky.
At the speed of sound.
Andrew, would you like to transcribe all the light?
No,
you're
I'd like to
seeing
know
in
how to do
sound?
number 48.
This all makes sense in just a second.
I-
I'm trying to work on it.
You don't want to transcribe a piece of music.
So when
So
do you
I
always
want
get
to
like
harmonize it
before
into sound by the way things are complex.
Not all bullets go. But kind of.
A lot, yeah, most. So you must get hit by the bullet.
Yes.
Well,
So-
it depends how far you are away from. Well, no, I'm stupid.
I
hate
I don't think moving.
Would you like to transcribe?
Yeah.
No, yeah, 'cause I feel like,
Why not?
except the whole standoff thing
You
still
don't want
makes
to hear
sense.
the light.
That actually makes it make more sense. Get shot and still shoot
No, I'm
it.
trying to see your algebra equations.
Or just die instead. So like,
Ignore that. This is the one.
wait until they shoot. Like,
That's,
you
that's
shoot.
more way for them.
That's visual.
No, I don't mean like,
Oh, you did get the right answer. Good job.
I mean.
I think that's the right answer. But now I have to figure out how the bloody heck you did that.
Like, somebody
Okay.
has a gun.
Okay.
So,
Oh, I kind of see.
Antonyms.
so quick summary and how this deal is going to play out with what I just did. And we're going to go back and we're going to look at what's going to happen with the slinky. So antinodes, you have nodes which are points where you have no movement, and then you have like antinodes where you have maximum movement. Okay, so that's one of the key things you have to keep track of in terms of terminology.
You mean?
So
Oh.
the simplest harmonic, this is what I'm going to show you, is that I'm just going to make this thing oscillate back and forth where you have one antinode. So if that's the case, so as this thing is like up here, so it takes a little bit of leap of faith with this one. So imagine that you've got this up here as like the top half of the wavelength. And then you would have that one over here coming back over here. So this, and I'm never going to expect you to memorize this, but if you think about it, the equation just makes sense. So to get the wavelength, it's 2L over M. So in this situation, you have one antinode. It isn't the nodes, it's the number of antinodes. So I've got one antinode vibrating in here like this. So if I take 2L and divide it by 1, I just get 2L. So the wavelength then is going to be twice this confined space. Okay? Because I've got half of a wavelength here, and then I have the other one, if you can imagine, being out here on the other side. So if you set this one up where you have two antinodes, okay? So if you go back to that same formula, okay, I've got 2L. The 2L on the top never changes. That's always the same thing. So I've got 2L, but now I have two antinodes. Well, now the wavelength just becomes the length of the box, okay? And so that's as simple as it can get. So then if you have 3, if you have 4. So here's the point. As you increase the number of antinodes, what's going to happen to the wavelength? It's going to become smaller and smaller and smaller. But what's going to happen to the frequency?
It's going to get higher.
Frequency is going to get higher and higher and higher. And so is the energy that it's going to take to shake this spring. So down here, this is kind of what I'm showing you here. So if you look at frequency equaling the velocity divided by the wavelength, okay? And all I did instead of wavelength, I put 2L. Because this is how, in this situation, you have m equals 1, then that wavelength is going to be 2L. So this ratio of the speed of sound, which is going to be invariant, or the speed of the slinky, or whatever it is, that's a fixed value. So is the length of that of whatever you're making vibrate. So that's a fixed value. So basically, to get that frequency, when you just have that one where it's just that simple amplitude where that length is 2L, oh, your frequency is going to be 1/2 that ratio of your velocity to your length. Now, here's what's important. Then when I go to m equals 2, now that's going to be just V over L. Because when I'm doing that, oh, that's going to happen to this L. Well, look, I'm going from the frequency being 1/2 VL to the frequency VL. So my wavelength is getting shorter, but what's happening to my frequency? It's doubling. So it's going to double because we went from 1/2 of VL to VL. So then if I go to where m equals 3, again, look what's happening to the frequency. The frequency is going up, the wavelength is getting shorter, it takes more and more energy. So to show that, so come back here real quick. He's back.
He's back.
He's back in Slinkies. Okay, Bruce, let's. Okay, so.
I was proving a point.
What point?
Show.
Equals.
What happened? What happened here?
Wavelength, half a wavelength. So, yeah. Okay, node, 2 antinodes. Okay, so if we make this as simple as it possibly can get, okay, so this length is what's defining this structure of this set of conditions. So right now, how much of that wavelength is there between Bruce and I?
1 or half.
Half. So to get the entire wavelength, I would double this.
Yeah.
So now, but here's what's going to be important, and this is going to play out even when we get to this idea of like a structure and how you define the system. The same idea is going to play out even when we get to electrons moving around the nucleus of an atom. How you define the system is going to define the harmony and the length and the frequency that this thing is going to vibrate at. Because if I move a lot closer, okay, and I change the system, okay, now what's happened to the wavelength? It's become shorter. So if I change the condition, I'm going to change the harmonic. Okay? So when you look at, well, remember this when we get into structures of atoms. So if you look at an electron, you figured out the electrons actually move in waves. So the fundamental wavelength that an electron can have is the diameter of a hydrogen atom, because it's only going to move within the confines of that structure. Then you can double the wavelength, so now I can go like, hold on. Actually, hold on. There we go. Okay? So now I've got this going, right? So this, how much of the wavelength do I have right now?
1.
How many antinodes? 2. But what's happened to my frequency? Frequency has, by what factor?
2.
Yeah, I've doubled it. Now, if I go like this, hold on.
That looks about 4, right?
Now how many antinodes do I have? 4. So with 4 antinodes, how many wavelengths do I have in there? 2. But the frequency then has gone way, way up. So now if I try to do something really, really fast like this, okay? All right?
6 or 8?
I think that was 6.
Let's go with 6, okay? But here's the point. I've greatly increased the number of antinodes. What's happened to the wavelength? wavelength has gone way, way down, but the frequency has gone way, way up, and my energy it took to input it went way, way up. Okay, let go. So, back we go.
Good, Isaac. I was almost there when I should be. Here, I got it. Are there any other ones you needed help with?
Ben apologized to him now. He abused that now.
I cannot believe it.
Let me erase my question mark on this one.
Got a Sharpie in all that.
That's what I tried to do. I think that's shorter than.
No, every
That's very much too much. Oh, 30.
smaller base time. I say,
I didn't think that was
base
what I
size
said.
for every
Shorter.
ladies and gentlemen.
Let's look at 30. Hold on.
Hey, we're allowed to add.
That's it, right? Like, you just the one person, but then it's Jason.
Oh, yeah, he is.
They're super baggy
What's his
too.
GPA?
Yeah.
Honestly, look up. How's it that high?
You did.
Okay.
Oh. That's exactly how they made the GPA.
First of all, this is millimeters, so that's going to be a 0.0 something.
Okay. So,
Otherwise, that's
this equation's in your book. Again, you just have to know how to use it. This is going to form the basis of the lab we're going to do on Tuesday, because I'm actually going to have a whole bunch of these set up, and you're going to try and figure out like the wavelength of the sound. So, if it's an open system like this, so here's the dichotomy about this. You're talking about a sound wave that's actually like a longitudinal wave, but we represent it visually in terms of a transverse wave, because it's easy to see how that's going to play out. It's actually a longitudinal wave, but we draw it as a transverse wave.
I did not see that.
So on an open system, like the Ames tube, okay? So with an open system, where you get this harmonic, where it begins to vibrate, is that it's the wavelength of the sound divided by 2. Because if you look at how I drew this, imagine that you've got like half of an antinode here, or an antinode here, and then you're coming in here like this. So this is like half the wavelength. So the entire wavelength would be out here. So if it's an open system, you're starting here, it's coming in, that's going to be that whole thing. So this is why on an open system, the length of that tube is going to be half your wavelength. So think this through. If you want to have a shorter tube, what do you want to have happen to your wavelength that you produce?
Make it shorter.
With the wavelength shorter, to make the wavelength shorter, what would you do with the frequency of the sound though? Yeah, you would make that frequency higher. So this is why with that Ames tube, I can only work off of a specific length based upon that wavelength. Because if the wavelength is too long or the wavelength is too short, it won't resonate within that structure. So this is why it will only work with a very, very specific frequency. Now, on an open-closed system, this takes a little bit more of a leap of faith. And again, we're drawing this as a transverse wave, but in reality it's a longitudinal wave. So, but imagine that this is why this thing is L/4. So with this one, imagine that you're starting here. Here's like the first quarter of the wave, and then it would come down here, and then it would come up, and then you would end up over here. So with this one, this is why on an open-closed system, the wavelength is a 4. So this is why, like when I did this one, okay, with that much shorter, okay, so I get that point of resonance, but notice that if you look at this tube, so this is with the 880, So this is pretty short. But if you look at that Ames tube, where that vibrates on an open system, notice that this is a lot longer. So this is representing half of a wavelength from here, but when I do it with this, it's representing a fourth of that, and so it's actually kind of close. So if you look at where that was resonating, okay, which was about right there, so that's about half the length of that Ames tube. So with an open system, you get half of it. With an open-closed system, you get a fourth of it. And so you can kind of visually see that difference with that tuning fork. Okay, now the other thing about this is when you get into harmonics, these only work on odd numbers of harmonics. This is going to be one of the questions on your assignment. It says this will only work on odds. Those work on all of those, 1, 2, 3, and 4. Because of the fact that you're dealing with like a fourth of it, where it has to like reinforce itself again further out, this will only work with harmonics of 1, 3, and 5 in terms of this length. So if this length is, say, 10 centimeters, then it would work at 10 centimeters, it would work at 30 centimeters, it would work at 50 centimeters, where you would multiply that by that length. Whereas those, it would work at like 10, 20, 30, 40. There you go. So, okay, I am done. Exhaustive lecture. Boomer. Really?
I've heard this line before. Boomer is a state of mind, not how old you are.
Well, I've been told I was born with an old soul, so.
So you just admitted it.
Yeah. Well, all of my siblings are boomers, so,
Oh,
and I have lost.
So he was raised in a house.
This is bad.
oh, he just said this is bad.
No. For the,
Yeah,
it doesn't go there. It's
Did you set it down on the ground before the demo?
because millennials is why he'd be X like my parents.
hold on, stop that for a second while I find my thing.